Okay, this is one of the first videos that I'm doing on thermal radiation, and I'm going to introduce you to a couple of terms related to thermal radiation. Essentially, we're going to talk of absorbing power. We're going to talk of absorbing power. Let us begin with an example. Let us say we have an object. Right? Let us say this is an object, and this is a source of radiation, and this object is emitting radiant energy. Right? So these are all radiations coming out of this object and are incident upon this particular surface of the object. Now, the radiant energy which is incident upon this gets divided into three parts. One part, let me mention it over here. One part gets absorbed, a part of it gets absorbed, a part of it gets reflected, and a part of it gets transmitted. Right? I think this is quite logical and understandable. Energy which is incident on this surface, part of it will get absorbed, part of it will get reflected back, and part of it will get transmitted. And that's the basis for absorbing power. Absorbing power is denoted by small a and is given by Q1 upon Q. Right? Here Q is the total energy, radiant energy incident upon the object. Right? So Q is the total energy incident upon object, and Q1 is the energy absorbed. Q1 is the energy absorbed. So absorbing power is a ratio of energy absorbed to total energy incident. Right? Let us take some values. So let us say Q1 total energy incident is, say for example, 60 joules, because it's energy, it's radiant energy. So I can take the unit 60 joules over here, and energy absorbed, let us say, I'm just taking random values, 40 joules. So A will turn out to be 40 upon 60, so that'll get a value of 2 by 3. So the absorbing power is 2 by 3. Right? Similarly, if I denote the energy reflected by, say, Q2, then reflecting power of the surface of the object, reflecting power, which will be denoted by R, will be Q2 upon Q. The total energy absorbed, the total energy incident is still the same, out of which small part Q2 is reflected. Let us again take random value, say 10 joules is reflected back and incident is 60 joules. So I'll get a value of 1 by 6. So reflecting power will be 1 by 6. And similarly, if energy transmitted, I denote it by Q3, then transmitting power T will be Q3 upon Q, and this will turn out to be, since 40 joule and 10 joule has already been used up, so I'm left with 10 joules. So 10 joules is transmitted and total incident is 60 joules, so I gain a value of 1 by 6. So I've got three things. One is absorbing power, two is reflecting power, I should use the reflecting power, and third is transmitting power. Q1 by Q, Q2 by Q, and Q3 by Q, right, and denoted by ART. So if I take the sum of A plus R plus T, that is the sum of absorbing power, reflecting power, and transmitting power, I'll get this as equal to Q1 upon Q plus Q2 upon Q plus Q3 upon Q, and this will be Q1 plus Q2 plus Q3 upon Q, and Q1 plus Q2 plus Q3 is Q, so this will give me a value of 1, because this will also be equal to 1. So A plus R plus T is equal to 1. The sum of absorbing power, reflecting power, and transmitting power turns out to be 1. Let us go back to absorbing power. Absorbing power is A is equal to Q1 upon Q, where we just say that Q1 is the energy absorbed. Q1 is energy absorbed and this is total incident energy. Now if I draw the diagram again over here, right, in the space I have over here, let us say this is an object and this is the source, and again I'm drawing the same incident radiations energy falling on this object. Now we say that 40 joules of energy was absorbed by the object, whereas 60 joules is the total energy, radiant energy incident upon this object. Now this 60 joules of radiant energy which is incident upon this particular object over here will comprise of different wavelengths. For example, the 60 joules could be from, let us say, 7,000 angstroms to, let us say, 10,000 angstroms. I'm just taking random value. This 60 joules of energy which is incident upon this can have any wavelength from, say, for example, 7,000 angstrom to 10,000 angstroms. Now the value of A will vary depending upon the range of wavelength we are taking. So let us say we are focusing our attention on the wavelength range of 8,000 angstroms to, say, 9,000 angstroms. This incidentally turns out to be the part of the visible spectrum. So say we are focusing on 8,000 angstroms to 9,000 angstroms. What may happen is that out of the 60 joules, this range could be, say, for example, this range could be 20 joules. I'm just taking a random value. And out of 60 joules which is incident, and out of these 20 joules maybe only 12 joules is absorbed. So this is incident, and say 10 joules is absorbed, and therefore I'll get a value of A as 10 upon 20, and that will be 0.5, right? Now if I take a different wavelength range, let us say this is up to, I have taken up to 10,000, so let us say I'm taking a range of 9,000 angstroms to 10,000 angstroms. 10,000 angstroms. For this could be something else. It is not necessarily it will be 20 joules, it could be something. Let us say it is 15 joules, right? 15 joules. And the energy absorbed, this is incident. This is total incident energy of this particular wavelength. Out of these 15 joules, the energy which is absorbed is not necessarily in the same ratio, is not half. It could be something else. It could be, say, for example, 9 joules. And therefore A will turn out to be 9 upon 15, which is 3 upon 5, which is nearly 0.6. Right? So we can see here that the value of A for different wavelength range is different. Right? So it is not necessary that the value of A is constant. Its value keeps on changing for different values of wavelength range. And therefore what we do is we introduce or bring in another term, or we need a different term to explain or understand absorbing power, and therefore the term that we bring in is spectral absorbing power. Spectral absorbing power, which we will denote by A lambda. Right? So this symbol A lambda indicates that we are talking of spectral absorbing power, and A lambda is given by, right? It's again a ratio. It's a ratio of the amount of energy absorbed of a certain wavelength range to total energy incident of the same wavelength range. Right. So as we saw in the previous example, the amount of energy absorbed of certain wavelength range, for example, we took the value of 8,000 to 9,000 angstrom, and total energy incident was 20 joules, out of which 10 joule was absorbed for that particular wavelength range. Right. So A lambda is for a specific wavelength range, right, whereas A was not specifying a particular wavelength range. And of course, when we take these ratios, when we take the amount of energy absorbed, the time has to be same. That means that if we are taking 10 seconds to measure the amount of energy absorbed, total energy incident also should be considered for 10 seconds. So this is the definition of A lambda, and therefore we also come to the equation A is equal to integration of A lambda d lambda, because A is for the entire wavelength range, whereas A lambda is for a specific range. So if I keep on getting value of A lambda for small wavelength ranges and integrate them over the entire range, I'll get the total absorbing power. Right? Okay, before I end this video, I want to talk about a perfect black body. A perfect black body. A perfect black body is one which absorbs all the incident radiations falling on it. So if 60 joules of any particular wavelength is falling on it, right, it will absorb all the 60 joules, and therefore A lambda will be 60 upon 60 is equal to 1. So the value of A lambda will be 1 for a perfectly black body. This concept comes from the concept of light, because if you have an object which is a color black, it means that it is absorbing all the colors. Similarly, here also we are saying that if we are calling it a black body because it is absorbing all the radiations falling on it. So just keep in mind, for a perfect black body, A lambda absorbing power, spectral absorbing power is 1. In the next video, right, I'll be introducing you to the emissive power. We have talked of absorbing power in this video, and we will now be talking about emissive power in the next video. Right. Thank you.